Hi dear students, welcome to our YouTube channel Anveshika Andhra Pradesh. Today we are going to learn about spherical aberration. So here I have taken this convex lens and I am placing this convex lens here, and this is our light source. Now I will switch on the light source. And for clear vision I am also switch off the light. Now I am opening the slit slowly. Observe here all the parallel rays which are coming from the light source incident on the convex lens, and here after refraction all the rays meet at different points. See here. So again I am closing and opening the slit. Observe all the parallel rays incident on the lens, and after refraction different rays are focusing at different points. So why it is happening like this? Observe here, out of these 5 parallel rays, the middle ray which is passing through the center of this lens is going straight line path, which is not deviating, and it is exactly in a straight line path. So that's why this ray can be taken as principal axis of this convex lens. So here another 2 parallel rays very nearer to this principal axis. So these 2 parallel rays are called as paraxial rays, and the remaining these 2 rays, observe here, these 2 are incident on the edge of the convex lens or the rim of the convex lens. So these 2 rays are called as marginal rays. So observe, after the refraction these paraxial rays and the marginal rays are not focusing exactly at the same point. Here the marginal rays are focusing at principal axis very nearer to the convex lens, whereas these paraxial rays focusing on the principal axis far from the lens. So marginal rays are meeting nearer to the convex lens, whereas paraxial rays are meeting far from the convex lens. Now focus of these marginal rays can be taken as capital FM, and this is center of our convex lens. So the distance between this FM and the center of the lens gives the focal length of marginal rays, and this is focus point of paraxial rays, so it can be taken as capital FP, and the distance between this FP and the center of the convex lens gives the focal length of the paraxial rays. So clearly observe, the focal length of the marginal rays is less than the focal length of the paraxial rays. Thus the image is not sharp on the axis. So the failure or inability of lens to form point image of an axial point object is called spherical aberration. The reason of spherical aberration is different zones have different focal lengths, and marginal rays suffers greater deviation than the paraxial rays. Here the distance between FM and FP, or the focal lengths of marginal rays and the paraxial rays, is the measure of longitudinal spherical aberration. So here this is FM and this is FP. This distance gives the longitudinal spherical aberration. If we place a screen normal to the principal axis at FM, then the image on the screen is in the form of circular disc, and the disc would be sharply focused at the center but diffused near the outer edge. If the screen is moved between FM and FP, then the size of the disk is minimum in this position, where the paraxial rays and the marginal rays are crossed. See here, this one is marginal ray and this one is paraxial ray. This is one cross point and this is one marginal ray and this one is another paraxial ray. This is another cross point. Say it is A and it is B. Then the position at AB, we obtain the best possible uniform sharp image. This is called circle of least confusion. So here the diameter of the circle of least confusion, that is this AB, is the measure of the lateral spherical aberration or transverse spherical aberration. So how can we minimize this spherical aberration? There are many methods to minimize this aberration, but now I will show 4 methods only. The first one is by means of stops. Now I am placing the stops in the path of paraxial rays like this. So we get the focus of the marginal rays only. Similarly, if I place the stops in the path of marginal rays, we are getting focus point of the paraxial rays only. So in this way, by using the stops, we can get only one focus point either by paraxial rays or either by marginal rays. So in this way, we can minimize the spherical aberration by using stops. The second one is by the use of plano-convex lens. This is a plano-convex lens and this surface is plane surface and this one is convex surface. So observe here. Now I am placing this plano-convex lens like this. Then we are getting this spherical aberration like this. So if I rotate this plano-convex lens, the convex surface of the plano-convex lens towards the light source, then we can minimize the spherical aberration. So clearly observe here, all the rays are focusing at the same point. Now see the third method. Here we are taking 2 plano-convex lenses and placing the convex surfaces of the 2 plano-convex lenses towards the light source, and the distance between these 2 plano-convex lenses is the difference between the focal lengths of these 2 plano-convex lenses. Then also we can get this focus point of all the rays. So in this way, by placing these 2 plano-convex lenses, we can minimize the spherical aberration. For the last method, I have taken one convex lens and one concave lens and I am placing like this and I am opening the slit slowly. You observe how the parallel beam coming from the source incident on the lenses and after refraction how the spherical aberration is formed. For clear vision, I will switch off the light. So see here, the spherical aberration is formed due to convex lens in this side and due to concave lens it is formed this side. So the spherical aberration for convex lens is positive and for concave lens is negative. So if we place together like this, these positive and negative will be nullified and finally we can minimize the spherical aberration